you don't have to be a biogeographer to love the Santa Monica Mountains. I'll just say right up front, this is a beautiful place. One of the reasons we value this is because it's beautiful and we love living here. And it's important to learn what the rules are on this landscape so we can inhabit it and not get burned and not chew it up or destroy it in some quixotic attempt to produce fire safety in ineffective ways. So I'm going to try to stick mostly to these kind of talking points here. I guess one is more me and two is going to be more Kathy. So I'm going to tell you what we've got sort of ecologically here, why we might care about it, what threatens it, and a little bit about how we can protect ourselves. So, there we go. I love this place. I guess you guys do too since you live here. I don't need to sell this point to anybody, but this is a special place, and it's special in sort of a bigger picture too. Let me take you up into space here. This is an image that was produced by NASA. We're here. Coast. Yeah, we're all right about there right now. This is just shows you the sort of relation of where the Santa Monica Mountains are in Southern California. We're part of the transverse range. There's a, if I step away from this mic, I can point. We'll do that. I'll just talk loud. This is the San Andreas Fault. It comes right up here, and everything west of that is basically seafloor that's been scraped up as the North American plate just kind of grinds northwest and pushes us all along, which is why there are marine fossils down the road from y'all. And oh, the laser pointer right on. Yeah, okay, there we are. Here's another kind of unusual view of this place. So it's part of the transverse range. So we're looking at, if you're at 100,000 feet looking down, you'd see something about like this. You can see we're part of this east-west trending range here. And the wind tends to come out of the north when the Santa Anas blow, so it blows right down these little canyons to the sea. And one thing you can't really see from this picture, which the next slide shows you pretty clearly, is that the Santa Monica Mountains are not nearly as high as the San Gabriels. Our mountains here top out at about 3,100 feet. We're down here, and this is the vertical relief here is tripled. The JPL made this image, just so you know. This is 3 times vertical relief, but the relative height is comparable. And this is important for fire because we don't really have any significant lightning starts down here in our mountains. The lightning that we get, like we did last week, tends to come in the wintertime when it's raining. It might burn one log. We actually had a fire started by lightning in the winter when it was raining a couple years ago at Circle X, and it burned one log. And the summer lightning, up from monsoon thunderstorms up in the San Gabriels can be a significant source of fire ignitions up there. And in prehistoric times, it may be the case that fire started up there and smoldered around until fall when the Santa Anas blew, and then they come down out of those mountains, whip all the way across the then undeveloped plains and up into the Santa Monicas. But that didn't happen very often. And all the historic evidence we've pulled together from various sources suggests that the natural fire return intervals in the Santa Monica Mountains were something on the order of every 70, maybe as much as every 100 years burn in any particular location. And so our mountains, I guess, they didn't see as much fire as they saw up in the high country there. And almost all of our fires are started by people. And there's more people around here than ever before, and we've got more fire in these mountains than ever before. And historically, there was a lot less fire in the Santa Monica Mountains. So we are very much in the business of fire prevention and fire suppression, and we don't really do any prescribed burning in these mountains anymore because there's no resource benefit to doing that. We now know that we have more fire than our ecosystems can handle, and giving it more is pushing it the wrong way. We need better fire protection here and stretch out the intervals between fires so our vegetation can recover. There are lots of other parts of the world, places like a lot of the forests in the Sierras, and even up in the San Gabriels for that matter, where there was effective fire suppression over the course of most of the 20th century, and we allowed forests to grow up more densely than is natural and leaf litter to build up more deeply than is natural. And in places like that, thinning and prescribed burning today does have resource benefit, and there's an awful lot of work to do out there. We've created that problem on huge acreages. But the great news about the Southern California coastal shrublands in general, and the Santa Monica Mountains in particular, is that is not our problem here, and we don't have to deal with that one. The problem, though, is that it's naturally a very flammable landscape, and we all have to learn how to live with that. This is another figure that relates to the lightning. Let's see if I can show you where we are. So if you can see the coast here, Santa Monica Mountains are like up here. This shows you how moist air pushes inland during monsoons. And in places where you get convergence, air coming together in the summer when you've got unstable air, that's where you get thunderstorms starting. So this is kind of a map of the natural causes of summertime lightning. And you can see it's up here in the mountains in a lot of places, and it's not down here in the Santa Monica Mountains. So it's not the kind of fire we have to worry about. Our mountains are high enough to create kind of an orographic precipitation gradient. This map shows you basically the cooler colors are more rain. There's almost twice as much rain up at the top of the mountains than there is down at the beach. If you live up at Circle X Ranch out here at the west end, kind of in the middle of this blue thing here, and check your rain gauge, it's going to have a lot more rain in it than if you had one in your backyard down here at Zuma, out on Doom, at Big Doom Point. And this is a very generalized map of vegetation. We've produced a beautiful, highly detailed map of the vegetation of the Santa Monica Mountains over the course of the last decade, which we can do all kinds of things with. And it's available to the public, and you guys can do lots of things with it too. I do a lot of fire modeling with it, among other things. But I just point out to you here that pink is coastal sage scrub, and it kind of occurs at lower elevations, and green is this big chaparral band at higher elevations. The yellow is grasslands. We've got a lot of grasslands inland. There's a lot of microclimates in the Santa Monica Mountains. You might recall a few years ago when we set the highest temperature record ever in LA County over here in Woodland Hills in July, a mere 10 miles from the beach, and it was 119 degrees, I think. Is that what it got to? And there's a very strong coastal to inland sort of climate gradient that has a lot of effect on our vegetation. And y'all know, I suppose, that most of our rain comes in the winter. We get these glorious low-pressure systems. We're down here, and these things wind up in the North Pacific and come plowing in and give us rain most years. And then every single year, we know that it dries out. You know, this is a Mediterranean climate, so we have this 6-month annual seasonal drought that we call summer, basically. So every year can be a big fire year in the Santa Monica Mountains. You know, in years when we get extra rain in the winter, you know, our fire guys will tell us, oh, you know, a lot of fine fuels grew this winter. This could be a big fire year, you know. And then in a dry year like this year, you know, we go out there and look and say, oh, live fuel moistures are really low. You know, this could be a big fire year. And basically, every year, you know, we get the conditions for a big fire. And it's just a question of whether it happens during our Santa Ana winds. And this has been going on for a long time. So our landscape is naturally flammable. We have not created an unnaturally flammable situation here. That's the good news, such as it is. But look, here's a fire, the Malibu Canyon fire in 1917 and the Malibu Canyon fire in 2007 from approximately the same vantage point. And times change, but some things remain the same. So this is the landscape we inhabit, and you know, we need to live with these kind of fires. In fact, with as many people as are here now, we start more fires than ever before, and so better fire prevention is in order and will benefit us some. I just want to tell you just a little bit about climate here. Mediterranean climate is special. The whole world doesn't do this. It's peculiar to this area and a few other places. Just bore you a little bit with the graph. If you can imagine, this is a calendar year from January, February, March through December. And they map, this is kind of a clever way to do this. You've got temperature in a dotted line here, so it's cool in the winter and hot in the summer. And then this is precipitation, it rains in the winter. And here's that 6-month drought called summer. And the stippled area here is when temperatures are high and rainfall is low. That's basically, there's our annual drought every year. And right at the end of this annual drought is when the Santa Ana winds start blowing. So other areas aren't like this. This is what other parts of the world look like. So here's our Mediterranean climate over here, right? So a rainforest, it'd look like this. You know, it's warm all the time. It rains like hell all the time. If you lived in Michigan, it'd look about like this. You know, it's warm in the summer and cold in the winter and rains pretty much all year long. Tundra up here, if you're up in Barrow, Alaska, you know, summer's this time when it cracks above zero for about 2 months. And this is Brawley, California. If you live out in the desert, you know, it rains hardly ever and it's hotter than hell. And, you know, it's almost always a drought because it's the desert. This is Astoria, Oregon. You know, if you lived up there, it rains like hell all the time. You know, summer up there is like 3 days in the middle of July, you know, when the sun comes out and then it rains, you know. And here's the Mediterranean climate. So, you know, we are different. And it's special. And things that live here are different as a result of that. Turns out there are 5 Mediterranean climate zones in the world, and they're all in places I really want to visit. They're really beautiful places to speed this presentation along. I took out the little round the world in 45 seconds thing I was going to do for you here, but I'll just point out that most of these Mediterranean climate zones are about the same latitude, north and south. They're kind of between 30 and 45 north and south latitude, and that's because, well, I'm not going to take the time to do this. Those are warm, dry places around the world because of global circulation patterns. Air is descending there, so you tend to get persistent high pressure at those locations. And of course, we call it Mediterranean climate because the Mediterranean basin is like that, but also here we are in California. Central Chile does this. Western Cape, South Africa does that, and a couple places in western South Australia do this. And the vegetation in each of these places kind of looks the same if you don't get too close to it. It's short kind of shrublands. A lot of the plants are, it's an example of what we call convergent evolution, when plants and animals solve the same kind of ecological problems to live in an environment, but they develop it independently. You know, if you gave a whole bunch of people a problem to solve and they all had to solve it, some of them would solve it in the same kind of way. But you tend to get completely different species in all of these places. So there are also biogeographic hotspots. It turns out if you go around the world and map species diversity, you'll find some places that got a lot more species than others, and there are often places that have locally endemic species, species that occur in a local area and not anywhere else. And if you notice, pretty much all those Mediterranean climate zones are on this map of the top 25 global hotspots of biodiversity that was worked up in a paper a couple of years ago. Like half of the world's species live in about 2% of the world's landscape here. They considered not only species richness, but also the endangered nature of these sites. So these are places that have a lot of species richness and also a lot of development or other things that are destroying habitat. And the only one of Mediterranean climates that didn't make the list is that South Australia patch right there. And I think that's just because that's a very remote place and there's not that much development going on there. I'd point out that the California floristic province, of which we're all part, is in the top 10, which means we're kicking biodiversity butt on Chile and the Mediterranean and South Africa and Africa. Not that we're competing, but if we were. And by the way, you know, the National Park Service started in our country, and dozens of other nations around the world have emulated it and created national parks of their own. And folks in these areas have all set up national park systems to try to preserve some of their local national heritage, and they look to us to show them the way. And if we solve, you know, persistent resource management problems here about how people can live on these landscapes and preserve them and not destroy the natural resource to make themselves safe and not accidentally destroy it by making too much fire, you know, those kind of things are issues for them too. And so it's a little overly dramatic perhaps to say the world is watching us, but you know, in a sense they are, and we, you know. We want to help them too. We're not competing with them. We're trying to help everybody succeed, and they're all keenly interested in how we do this. I before I move on from talking about biodiversity, I'd also point out that we have new species moving into our landscape constantly. This is a map of exotic plants turning up in the state of California from 1850 to the present, and they turn up at a fairly steady rate of about a little more than 10 a year. Most of them are no big deal. It's like, oh great, more biodiversity, you know, nice little plant that can fit into the landscape. But some of them are really persistent, really invasive. Yeah, thank you. I could use a more pejorative word, imperialistic or something. You know, they're plants that really come in and take over the place, change ecosystem functions. Perhaps the ones we deal with mostly are actually annual grasses that wildly change the potential for fire in our landscape because they dry out very early in the season. They produce continuous beds of fine fuels that make great places to start a fire and to propagate a fire. And fires burn in California where these exotic annual grasses have established in places like our deserts, the Mojave Desert, that never used to see fire because the natural vegetation was discontinuous and couldn't really support fire, but now it can. And those kind of things are a real management problem in the Santa Monica Mountains. They grow on our fire breaks. They grow anywhere you scratch the ground, basically. They come back every single year, and it's one of the management things we're up against, and it's something the Indians never had to deal with. These species were not here back when we were all Chumash villages and burning the hill behind our hut to, you know, get some straight twigs to make baskets with next year. It's really been a game-changing kind of thing, and there's no apparent end in sight. These species will keep coming, and they're an ongoing management challenge. So let's see, this is just a real, I'm going to tell you a little bit about Santa Ana winds, and I'm going to kind of segue out of climate here and into winds, because that's the thing I haven't really talked about yet. So this looks like that Mediterranean climate graph I showed you all a few minutes ago. This is January, this is LA, so this is our local station here. So there's, the bars are rain, this is minimum and maximum temperatures. So, you know, there's our 6-month summer drought. So on about September, October, things are getting real dry. This is data that my colleagues at LA County have been collecting for a generation or two now. They go out behind their fire stations in various places around the county and snip twigs off of various designated shrubs every 2 weeks and weigh them and dry them and weigh them and calculate the live fuel moisture. And they track it because it's a real important predictor of fire behavior. And this black line here is a long-term average, and these other two are yearly values. So I guess one thing to see here is the long-term average is, this is January, so we have real high fuel moisture winter into spring, and it's very hard to start a fire when you have high fuel moisture. If you've ever tried to make a campfire with wet wood, you can appreciate that. It takes a lot of heat to drive moisture out of fuel before it can burn, and so fires don't burn real well under those kind of conditions. And then as the year goes on, it gets real dry, and this is the 60% line here. Firefighters view the world as fuel. Fuel is kind of the center of their world, so when they say the fuel moisture is 100%, you might think, how could that be? Does that mean it's a glass of water? It means that if you were to take the fuel and then weigh it and then dry it down again, what is it? It's what you'd consider 50%, I guess, if you weren't a firefighter. So we can now do 60%, which is really, you could think of it as 30%, I guess, if you think about this a different way. But in any case, this is a real critical level for them, and they say that when you hit that level, live fuels burn just like dead fuels, which is just kind of a rule of thumb. It may actually be the case that it gets really bad up around 80%. I was part of a research project that demonstrated we get really big fires starting at higher moistures than that. But every year in the fall, our fuel moistures are really low, so we're setting the stage for a big fire. Now this graph down here at the bottom shows you this blue line is the number of fires by month. So this is the spring when it's too moist for fires to do much. We have very few fires until about April when things start to dry out, and then we start getting more fires. The bars are how many acres burned in that month if you add them up through our whole fire history. And so these early fires, there's a lot of fires by June, July, but they're not adding up to a whole lot of acres. They're real small fires. But on towards September, October, when things get really dry, suddenly all hell breaks loose. There's actually fewer fires out here than there were a month or two before, but they're really big fires. And the reason, it's partly because of this fuel, but it's because this is when the Santa Ana winds kick in. And Santa Ana winds totally change everything. And Santa Ana winds make it possible to have fires that are 3 orders of magnitude bigger than would be without those winds. And those kind of fires completely determine our landscape. Almost every acre that burns out there burns in a Santa Ana wind-driven fire in the month of October, basically. More than half of all acres that burn in the month of October. And 97% of all the acres that burn between September and December, and that's because of Santa Ana winds. This is just to give you a bigger view of that. Really, the month of October, is the kicker. That's when live fuel moistures are still really low and the winds are coming on. It hasn't started raining yet, there's another attempt to visualize this. I'll confuse you here. This is a water year. If you ever noticed when they track water records for the state, they don't start in January, they start in July. Starting with July 1. So I've got this July through December to June. So if you imagine we've cut a year in half and put the back end on the front end. So here's our big fire season in the fall here. These are that same bars I was showing you on the last graph, the mean area burned. And up here, this is the mean number of Santa Ana wind days. So the Santa Ana winds start kicking in about September, and then you get a whole bunch of Santa Anas. In fact, you've got Santa Anas going into November, December, even January, February, but our acres of fire burn drops way off because the fuel moisture comes down. This is the Keach-Byram Drought Index, which is something firefighters and others sometimes calculate. It's sort of a cumulative, it's sort of a proxy for fuel moisture. And if it's up above about 400, you can have fires. When it falls below about 400, you pretty much can't have fires. And if you look at where 400 falls, it's just about at the end of fire season. So this little window here, when those Santa Ana winds are kicking in and the fuel moistures, the drought index is still quite high. That's where all this stuff happens. There's more you could say about that with regards to climate change, but I think I'll save that for another day and sake of time here. So let's talk about Santa Anas a little bit. You guys are all familiar with Santa Anas. You live here. You've seen a few. I don't know if you exactly know how they form, so I'll just take you through that briefly. It's a little cartoon to show you how they form. They form when you get high pressure sitting over these high elevation interior desert plains, and you get a low off the coast, and then they come spilling down to the coast. And as they descend to the coast, they start out cold and dry, or maybe kind of warmish and dry, and as they descend, they just get drier and warmer and drier and warmer. They expand adiabatically, and by the time you get down to the beach, they're really warm and really dry. On a Santa Ana wind day, often the highest temperature in the county will be reported like on the beach somewhere, and it's just worst case fire weather. They blow a lot. They get channeled by our terrain. They come funneling through those passes and canyons, and some places are a lot windier than others, and here we are. There's a little bit of good news here for you right here in Topanga. I guess if you think about it, Topanga's just kind of on the edge of this one. It's quite a bit windier west of here than, and you guys are maybe kind of in the not super windy end of the mountains here. There's a little bit of comfort in that. It may possibly be the case that one of the reasons we haven't had that big fire quite so recently here in Topanga is because we're not quite right in the wind corridors that occurred just west of us. The Las Virgenes corridor has seen an awful lot more fire than Topanga has in the last century, and this probably has something to do with it. I've done a lot of modeling with wind that I'm not going to have time to show you tonight, but I've got a couple of moving satellite pictures here that really give you a sense of this. You can really see, remember I was talking about high pressure being centered over here? Air goes clockwise around high pressure, and so you can see that stuff clocking around here. It's coming, the high pressure is probably up there about where the NV is for Nevada, and they'll be low down here somewhere and get this kind of salad shooter effect. That one's going this way, this one's going that way, and they're going offshore. You get a little bit of smoke in the air, and you can really see it. This is 2003. This is during the wildfires in 2003. Here's during the wildfires in 2007. You can kind of get that same thing. You know, it looks, when I look at this, it really strikes me, that looks a lot like when you blow a candle out on your table and a little bit of wisp of smoke comes off it for a little bit, you know. That property of smoke kind of scales up. But on the ground, this is a scary conflagration. So this is what, October 22nd, 2007. So here we are up here. This would have been just as the Canyon Fire was starting to wind down and these other big ones kicked off. If you recall, 2007 started with the Canyon Fire, and then the whole rest of the Southern California went off in the next week. Here's another, this is the next day. So anyway, this is, you know, these are the Santa Ana winds. You can't really see wind unless you get something up in the air, but you get a little bit of smoke in the air and you can see exactly what they're doing. So these are a force of nature, and they have been here for millions of years. These set up as a result of global kind of circulation patterns where the Pacific High sits. It's presumably been sitting there for millions of years, and this is a condition that we didn't create, and it's not unnatural, and it's not going away anytime soon, and we just need to live with this. We get this kind of weather predictably annually. Good news, such as it is that some climate modeling suggests that with climate change, if it changes the way we think it's going to change, Santa Ana's may become a little less intense in the future. We'll take the good news where we can find it. We're also going to probably get more variable precipitation, which will create greater potential for droughts, which also sets the stage for fire. Drought is natural in Mediterranean climates in general and in Southern California, and climatologists have documented these sort of cyclical kind of climate patterns on a number of time scales. This is the Pacific Decadal Oscillation, PDO. So this is an oscillation on time scale of like decades. This goes from 1650 up to now. The dotted lines here show the time period during which we have actual climate data. This is actual precipitation data, and this line going back is tree ring chronologies, and tree rings correlate really well with precipitation, and we demonstrate that up here, so you can extrapolate back. And so we have these periodic bad droughts, and they're natural. We didn't cause these, and every one of those is a potentially disastrous fire year. And we also have these years that are giant gully washers when the alluvial plains that we've built our cities on get built up by stuff coming out of the mountains. These are monthly values for the PDO index just in the 20th century, and so we have drier decades and wetter decades, and this shows actually some correlations with that fire history back there if you look at those maps. And we all know about El Nino. This is El Nino up here. When El Nino for us tends to mean a wetter year, and then we've got these La Nina events when the Pacific high pressure kind of moves up here and blocks the storms and forces them to go high around us, and we have a dry time in Southern California. So this is something that can happen like on a time scale of like 1 year. These occur in every couple of years. And our weather guys are always trying to tell us if next year is going to be one or the other of these. So again, these are natural things that affect the fuel moisture, affect our fire regime, and this is part of the environment that we live in. And we have some ability to forecast and model these things now. We know how this works, but on the ground, we still have to deal with the consequences of this. And this is why our fire regime is natural, and why it's not going away, and why we need to learn to live with it is we live with earthquakes and other kinds of things that we can't control or stop, but can learn to adapt to and survive. I'm talking a lot about drought. Something you can see right around here. This picture was taken down Topanga Canyon Road a little bit kind of on the way down to the coast, go south. Some of our more drought-sensitive shrubs will die back in in a drought year. This, I think, is mostly Ceanothus megacarpus that's dead here. Fire guys will tell you that dead fuels tend to be quite a bit drier than live fuels. So the more dead fuel you've got on your landscape, the more potential you've got for extreme fire behavior. There's some speculation that dead fuel may be especially well suited to making embers. You might actually get more embers out of this kind of material. I think they haven't fully demonstrated that yet, but it kind of seems likely, makes sense. We may be able to document that at some point. And so this stuff will die, and it'll sit there until the next big fire, and when the fire comes through, we'll have more extreme fire behavior as a result. We can map this kind of vegetation using various means, but we can't really stop this process, and this is something that's happening right in our backyard here. And just to give you a little cheery news about the future, this is a global climate model which suggests that a couple of global climate models go the way they think they're going to go. We are in what looks like the hottest spot in the whole damn country in terms of having to deal with a real whammy in terms of changing precipitation, annual precipitation, I think is what this is keyed on here. I don't really have time to talk to you tonight. I've got some slides to show how even if our annual precipitation averages stay the same, if we change the timing of it, it'll have some substantial implications for our fire regime. So anyway, we do have a lot of fire here. There are certain parts of our landscape that burn a lot more frequently than other parts. These are the mountains. But if you imagine, take the fire history, and if I were to represent it by cutting out little translucent plastic tiles to the shape of every fire and laying them down here and stacking them up such that the more times something burned, the warmer color it gets. This is what you'd see. Imagine you're seeing through a translucent layer of all the fires that have hit this landscape. There's a spot right down here at the bottom of Solstice Canyon, bottom of Chaparral Canyon Road, that has burned 12 times since 1925. Another place up here has burned 12 times since 1925. This is up off of Santa Susana Pass Road here. Just to get you oriented, here's the 101, here's the 118, here's the 23. So Topanga's like over here. You guys haven't seen that much fire, but an awful lot of fire blows down the Las Virgenes corridor here. Santa Susana Pass is a real wind tunnel. The Santa Ana's really whipped through there. We've got some ready sources of ignition off of roads up here, and historically we've had a lot of roadside fire starts up there. And if y'all think back to 2005 and the Topanga fire, that called so because it started this end of Topanga Boulevard, not because it started anywhere near Topanga Canyon. It started right here. First thing it did was jump the 118 freeway, and the next thing it did was it jumped it back, 8-lane freeway. It blew through most of the Simi Hills here, and the question is always, are we going to get a break in the weather before it jumps the 101 or not? And we did get a break in the weather, so we held it at the 101. If the wind had kept blowing, it probably would have jumped that too. And when they blow down Las Virgenes to the beach, let's see, here's Malibu's at Las Virgenes Canyon here. What usually happens at some point is the sea breeze starts taking over, and the fires get blown, usually west, sometimes east. They kind of burn back up into the hills. And so the fires hit the beach, and they kind of spread out. So that's why this pattern's over here. But anyway, if you live on this landscape, you can spot where you are, and like the stock investment guys will tell you, past performance is no predictor of future performance, but in fire it sort of is, because this fire regime is determined by things that operated in the past and will continue to operate in the future, like where the wind corridors are with regard to our terrain, which hasn't changed, and where the ignition patterns start, which is usually a function of human development and activities, and that's not likely to change too much either. And so these areas that have burned again and again and again in the past are probably going to be the ones that burn again and again and again in the future, but nowhere on this landscape is safe. Everywhere can burn, and a lot of our fire colleagues are really concerned about the eastern Santa Monica Mountains out this way, where we haven't had that many fires. But all the conditions exist there for some disastrous kind of interface fire like Oakland in '91. And if you just happen to be just downwind of where the fire starts, it's not much comfort to think it's only going to happen once in 100 years. You still have to deal with it. Anyway, I got too much text on this slide, but this is kind of a bottom line kind of message here. Big fires will come, and they will keep coming. This is a Mediterranean climate with a landscape that's naturally very flammable. It's been like this for millennia, and we need to learn how to live on this landscape. We can't stop these any more than we can stop earthquakes, but we can build to survive them, and we can manage our landscape. We can practice fire suppression, and by studying where fires start and thinking about things we can do about that, we can do a better job of that than we have in the past. There are opportunities we haven't begun to exploit yet that could reduce our fire frequency. In any case, we can learn how to survive these fires, and you guys are really impressing me, frankly, the more I learn about what your local fire safe councils are up to. You guys seem to be well on your way on communications and all kinds of planning, and really commend you for that. Let's see, I'm just going to bop through a little bit of fire behavior here. This is where my presentation may get a little ragged. We'll see how I do. I need to bring it in for landing here anyway. We've learned that palm trees are terrific sources of embers, terrific places, very receptive to embers, and also terrific sources of embers once they get going. So these are kind of urban fuels that are implicated in a lot of extreme fire behavior in neighborhoods. I'm not sure how many palm trees y'all have up here in this canyon, but if you have one in your backyard, you might think about removing it. This is some local coastal sage scrub with a call box there, which gives you a good convenient estimate of size. This was 93. This was the old Topanga fire. Those are probably 12, 15-foot flame length, something like that. So like I said, naturally flammable landscape, burning with low live fuel moistures in the fall. This vegetation wasn't that old here. It might have, I don't know exactly where this picture was taken. This is not some old, decadent, overgrown stand of vegetation. This was just a nice, happy little stand of coastal sage scrub, but in these kind of conditions, it really burns like gangbusters. These fires are really big. They are way bigger than we are. They release many orders of magnitude more energy than we do with all of our little fire trucks and jets and helicopters and things like that. Can you see the helicopter in this picture? There's a helicopter in this picture. I saw it earlier. Well, okay. Anyway, you see the Hollywood sign there. You could. The idea was that these things are big. Let's see. I'm going to kind of bop through this. This is output from a program called Behave that we use to model expected fire behavior. Fires. I think I'll just kind of skip through these. These are things that would take longer to explain to you. But basically, in Santa Ana winds, you can get really big flame lengths that are sufficiently large that we can't do effective or safe direct attack on the fires, and we pretty much just have to stay out of the way and do indirect kind of attacks until the weather moderates. Kathy will probably tell you more about that, but firefighters will tell you that you can't get out in front of these. We basically take defensive positions and wait for a break in the weather, and people die if we do otherwise. And it's really important for homeowners to understand what we're up against, because you can't just expect firefighters to come up and save your butt in this kind of weather, because they can't do it either. We all need to get to a safe place and get out of the way, and there's a lot we can be doing on that. Animals tend to leave when fire happens. People tend to stand around and watch. Get to a safe place. I paired this with a picture of a deer running away from a fire that I took out for the sake of brevity, but it's really great fun to watch these fires. They're spectacular, but get to a safe zone first. These guys are in a pretty safe zone here. They're not wearing much protective equipment. There's a lot to be said about embers. Steve Quarles apparently is going to come talk next time. He's going to tell you all about embers. We used to worry a lot about direct flame impingement, and that can and does burn lots of houses down. But with a pretty modest amount of defensible space around your house, you can be safe from that. Turns out you don't really need more than like 100 feet. You clear beyond 100 feet, and you're really not getting yourself any additional fire safety in terms of flames impinging on your house unless you're in really crazy terrain. But embers can blow 1.5 miles ahead of the fire and start new fires anywhere that there's a receptive fuel bed. In the kind of relative humidities we get during these Santa Anas every fall, embers start with a very high probability if they land on anything that's flammable. And this is how houses burn down. And we have an increasingly good sense of this as we do postmortems after all these big Southern California fires. It really comes down to the embers. And there's an awful lot everybody needs to do to make their house super resistant to embers. And that's a take-home message that you guys can work on. Houses are often the most flammable thing around. Look at this house. The eucalyptus trees didn't catch on fire. The pine tree didn't catch on fire. The palm tree didn't catch on fire. The house with the flammable roof got ignited by an ember and caught on fire. And okay, let's see. These are fire suppression costs. Fire is very expensive to suppress. We spend an awful lot of money on suppression, and if certain prevention kind of projects seem a little expensive, if you stop one big fire, you may just be dollars ahead. People have some misconceptions about chaparral and its relationship to fire. This is a series of photographs taken by my colleague Steve Davis, a professor over at Pepperdine University, of a place up by Circle X Ranch at the west end of the park. This is kind of up close to the Mishimoka trailhead off the west end of the park. And this picture was taken just before the 93 fires. It burned up in the Green Meadow fire in 93 and was just about bare dirt. Next spring, it was solid flowers. This is kind of looks like mustard in this picture, but it's not. It's bleeding hearts. It's Dicentra. It's a native plant that is pretty much a fire follower. And then a few years later, 2006, it's all back. If you look at it, this shrub is that shrub, is that shrub. This little band of vegetation here, resprouted, they're still there. It's what they call an auto-successional system. Everything this plant community needs to recover after a fire is on site. It doesn't need to be recolonized from outside. Plants burn and resprout. Plants have various seed mechanisms that allow them to tell when a fire has occurred, and they seeds wake up they've been waiting in the soil for decades, and they can tell when a fire happens, and they flower afterwards, and it can come back. But this only works if you have fires that don't occur very often. If you have really short intervals between fires, you can screw this all up, because these plants need a certain amount of time to recover after a fire, and if you hit them again before they're back, it can do a lot of damage to them, and we understand a lot how that works now. So this is kind of a little cartoon of how that whole system might work. If you think of that last slide, there was our closed canopy. We burned it up, we're there, and then we can come down here. But if you burn too often, okay, actually this is telling us what happens if you burn too often. If you get back down to here and you burn repeatedly, it turns out intervals of about 6 to 12 years, those are kind of thresholds for some of our obligate seeding shrubs. They're gone. We've got a number of dominant species of Ceanothus, for example, that cannot resprout after a fire. They can only come back by growing as seeds, and it takes them a few years to get established. It might be like 6 or so years before they make their first flower and put even one seed back into the system, and it might be something on the order of 12 years before they really are beginning to contribute very much. And if you have multiple fires with intervals shorter than that, they're just gone. And Steve Davis has demonstrated clearly that the shorter the interval is, and the more times it happens, the more damaging it is. And these plants just vanish from our landscape locally, and they get replaced by other things, often weeds, which some of these weedy grasses, for example, create a bigger fire hazard than the chaparral they replaced. They dry out earlier in the year. They have more fine fuels. They're easier to start a fire in, and they're much more volatile. The fires are they change rate of spread dramatically when the wind blows on them. More firefighters have died in grass kind of fires than any other vegetation type. And last year we had some big examples of this going on in Texas, but it happens here too. This hill used to all look like this kind of vegetation. This is kind of down at the entrance to Pepperdine University. Turns out, what we got here? The top of this hill up here burned in 1970, and again in 85, and again in 93, and again in 96. And now it's kind of mostly weedy grasses. There's a couple of shrubs, vigorous sprouting shrubs. That's probably mostly laurel sumac, Melasma lorina. And the bottom of this hill burned less frequently. It burned in 1970 and in 85. So it had 15 years between fire, and it did okay. And up here, there was 15 years, and then 8 years to the next one, and then 2 years to the one after that. And we lost most of the shrubs up there. So this is, this whole hill looked like this in 1970. And you can see this kind of stuff going on all over our landscape. There's a lot of this in Malibu Canyon, which is that fire corridor I showed y'all. And there's a couple of historic pictures I took to sort of show you how this process goes. Ecologists call this type conversion, when one kind of type of vegetation, say a shrubland, gets converted to another type, say a weedy grassland. This is a picture up near Santa Susana Pass, up near the very east end of Simi Valley. This picture was taken 1934. This picture I took 75 years to the day after that, same site. This was done by the folks doing something called the Vegetation Type Map Survey, this Forest Service survey they did back in the Depression, and they took some notes. This was, it had burned some at this point, but it had pretty good sort of low cover of chaparral hair, sage-script species in the foreground, and today it's basically a weedy mess, and the only chaparral you see out on that hill are the melasmas that are still, that's like the champion resprouter of the Santa Monica Mountains. That one will be here after we're all gone. And so this is what type conversion looks like. We don't like to see this happen to our mountains. But here is the site. This is Dark Canyon. This is off of Piuma Road, kind of in central Santa Monica Mountains. And this is what ecological sustainability looks like. This is that picture, 1934. I took this one 69 years to the day later, same day of the year, January 30th. You can count the shrubs on the hill. I mean, this one is that one. This one is that one. This is a very conservative landscape. And this one is burned. How often does this burn? So this part, it's burned 3 times, but the intervals were, it burned and then it burned again 23 years later, and then it burned 27 years after that. So that's within the limits of resilience of the community. Chaparral can handle that. If it's longer than about 20 years, chaparral's great. It comes right back. And it did. So this is great. This is what ecological sustainability looks like. We want more of our mountains to look like this, and with a little bit of effective fire prevention and continued fire suppression, I mean, we want to push our landscape back towards this and away from that other state. Let's see, just one last slide of these. This is another historic one. This is kind of on the Rincon going up towards Carpinteria. If you drive out that way, you drive along these bluffs, and these immediate bluffs haven't burned once since this picture was taken. That 1930, this is 2007. I wasn't there on the same day, sorry about that, I couldn't do that. But up here we've got, this light gray stuff is mostly purple sage, and the dark stuff is lemonade berry, Rus integrifolia. And down here the lemonade berry is just about filled up the whole thing. About the only places you still see the purple sage are the places, they actually plowed here and tried to farm that for a little bit, and you can see that's kind of where these things were. So in a long absence of fire here, on a place where lemonade berry can grow, it kind of slowly spread out and filled in and just about dominates the system. So this is a natural kind of coastal sage scrub succession, if you want to think of it like that. One kind of coastal sage scrub naturally succeeding to another kind over a long period of time in a place where it's got some refuge from fire. If you go out to Santa Catalina Island, you'll see places like this out there too. The Channel Islands are another place where there are natural fire refugia. And so that's sort of one example of what our landscape might look like if it had less fire. There are places down at Point Loma that are looking a little bit like that too. A lot of our landscape hasn't been too long since the last fire. Remember, we got to go about 20 years before we're really in the safe, and like a third of our landscape is in jeopardy right now this year if it got hit again. It's had a fire recently enough that it might be experiencing some damage from the next fire that it can't recover from. And so that's, as a resource manager, the National Park Service, we're always trying to think, when a fire happens, it's like, oh God, is there anything we can do to keep fire out of this place for another 20 years and let it come back? Because our landscape has a great potential to rejuvenate itself after fire if you can let it go 20 years between fires at the minimum. And remember, the historic return interval they thought was something on the order of 70. That would have been like way out here. We would have had a lot more old stuff. Some folks like to talk about old growth chaparral. My friend Ecology runs the Chaparral Institute in San Diego, goes around and takes pictures of it, and some people call it elfin forest. There are places in San Diego called elfin forest. If you can keep fire out of chaparral, some kinds for like 100 years, it kind of starts becoming sort of a nice place. It's not the impenetrable wall that we're all used to thinking about. It kind of starts to thin out the understory and kind of nice looking. Some of these old shrubs start looking like little trees. I've got a bunch of pictures of that I didn't include here for sake of brevity, but maybe I should stop there. That's probably a good place to stop. There's more I could show you, but I think this is a good stopping place. And I'd be happy to talk to folks later if you want to talk more about this stuff. And I think I'll turn over to, just can I field any questions right now? I'm not sure what our timing's looking like.
I know you were concerned about time, but could you say just a little bit about climate change and how that's going to affect all
Sure.
of us?
I'd be happy to. Let's see. Sure. The question is, could I speak briefly about possible implications of climate change and how that might affect our landscape? The general models are showing agreement that things are definitely going to be warmer. There's some question as to just how dry it's going to get. Things are likely to get a little drier than they are now, but most models suggest that our already naturally fairly variable climate is going to get even more variable. We are going to have more droughts and more really wet years and greater variation in our annual precipitation. That storm track can get a little wilder, and that could be pretty exciting. I haven't seen models yet that try to address timing of rain. I'm not sure if we can really do that yet, but if you think back to those slides I showed about the drought index and the Santa Anas when they come on, and how our real fire window is about 2-3 months long in the fall when the Santa Anas start coming on and before the rains come. Now imagine that the rains, same amount of rain every year, but imagine that rain came a month later. The Santa Anas are just continuing to ramp up and up and up in their frequency, and we could see a third more fire. If we increased our potential fire window by a third. If it went 2 months, it might double it. On the other hand, if the rains were to start coming a little earlier, same amount of rain, we could shut fire season down early and we could see a lot less fire. And I don't think anybody knows what that's going to do. So you might just have to live a really long time to begin to see that. The other thing sort of regionally for California that is suggested is as things warm up a little bit, more of our wintertime precipitation in the mountains is going to be rain and not snow, which is going to bode poorly for our state water supply, which is mostly based on snowmelt from the Sierras. If more of that falls as rain, we may be in the business of building more big honking reservoirs to try to capture that. We get a lot of great water out of that great Sierra snowpack that slowly melts and waters our rivers all summer long. And that's another implication that has been suggested.
Do we get that element that I think they've been exploring in Baja, where the difference between sort of a historic mosaic fire that gets put out a little faster, as opposed to the huge fires that just go on for miles and miles or hundreds of miles? Are we getting that in the Santa Monicas too?
That's a question it would take me several minutes to answer fully. I'll see if I can answer it briefly. You're referring to mostly to the work of Rich Minich, a professor out of UC Riverside who did a lot of fire history reconstruction from old air photos and other sources and produced some maps that showed, a lot more small-scale fire in northern Baja California relative to Southern California. And he suggested that in systems where it's dry enough that fuel accumulates relatively slowly, that a landscape's fire regime could actually be controlled by the rate of fuel accumulation, and it would be controlled by that and not by weather, by these Santa Ana winds, for example. And that kind of theory probably works better where it's dry down there than it does. The further north you go in California, the wetter things get, and plants grow better with more rain, and fuel accumulates at a greater rate. And so that fuel-limited kind of model works less well up here than it does down there. There are also a number of pretty valid criticisms that have been made of his methods. He had access to certain kinds of fire records in America that he didn't have access to south of the border, and a couple of those probably partly explain the historic pattern that he produced that's the basis of his work. It's also the case that under the influence of Santa Ana winds, fires can burn through vegetation of almost any age, and our big fires recently have shown again and again that that's true. In fact, one of the big fires we burned big in San Diego in 2003, the Cedar Fire, and then again in 2007. And I mean, there were places down there where, fires were burning through vegetation that was very young. I'm trying to think, there's this one place my colleagues talk about where fire blew through something that was 2 years old, kind of right by Highway 8, so there must have been a fire in between there. But it basically blew through a 2-year-old stand of mostly deerweed and then proceeded to jump an 8-lane freeway in a Santa Ana wind. And, under that kind of weather, all bets are off. And other folks have suggested that Santa Ana winds really are driving our fire regime, and that in Santa Ana winds, that kind of fuel model really doesn't work. And these big fires that we have seen in San Diego recently seem to support that. That's all stuff that's happened since Rich originally proposed those theories. And if his theories were true, those fires should have been stopping when they hit younger stands of vegetation, but they weren't. So I guess I'd say that theory generally has, I wouldn't say it's been completely discredited, but there's been additional evidence gathered that makes it a less strong hypothesis than was originally imagined. And folks used to talk about managing the Santa Monica Mountains like with some sort of big mosaic rotational burning kind of thing. And in a practical matter of natural resource management, we could never implement the kind of prescription that they were calling for anyway, because there's just not enough burn days here. There's not a lot of chaparral. You can't burn it safely. It won't burn under moderate conditions. You pretty much have to burn it in extreme weather to get it to go at all. And you can't burn it under extreme weather because you'll kill people, so we don't do that. And we used to have a fire management plan back in the 80s that said we were going to try to do that, and we realized we just couldn't do that. And we then later came to realize not only could we not do that, but it probably wasn't a good idea to do that. We now know that, what I was telling you earlier about the short fire return intervals can be very damaging to our vegetation. So we've got a number of reasons not to do that now. And I'd love to talk to you more about it if you want to hear a more complete answer. I think maybe I'll stop at that point. Thanks, y'all.